Every program eventually needs to save something: a game's progress, a user's settings, an object sitting in memory that has to survive after the program closes. But memory is just data your program understands while it's running. The moment you want to write that data to a file, send it over a network, or hand it to a completely different program, you hit a wall. Bytes in RAM aren't portable. That gap between what lives in memory and what can travel outside it is exactly what serialization exists to close. In this video, we'll break down what serialization actually is, walk through how it works step by step, compare the formats you'll actually encounter in real projects, and then get concrete about when you should reach for it and when you shouldn't. Let's get into it. Say you build a simple game character in your code: health, inventory, position, and equipped weapon. While your program runs, that character lives happily in memory as an object, a neat little structure your language understands natively. Close the program though, and that object is gone. Memory is volatile, it only exists while the process is alive. So you try the obvious thing: write the raw bytes of that object straight to a file. It doesn't work, at least not reliably. Objects in memory are full of pointers, memory addresses that only make sense inside that exact running program. Save those addresses to disk, reopen the file tomorrow, and they point at nothing. You need a format that describes the object's actual values, not where it happens to sit in RAM right now. That's the problem serialization was built to solve. Serialization is the process of converting an in-memory object into a format that can be stored or transmitted, usually a sequence of bytes or plain text, and then reconstructed later. The reverse process, turning that stored format back into a live object your program can use, is called deserialization. Think of it like packing a piece of furniture for shipping. The assembled chair, your object, doesn't fit through the mail slot. So you disassemble it into a flat-packed box following a set of instructions, ship it anywhere in the world, and on the other end, someone follows those same instructions in reverse to reassemble the exact same chair. Serialization is that flat-pack format. It strips an object down to its essential data in a shape any compatible program, even one written in a different language, can read back and rebuild. Here's the mechanical version. On the right side, a serializer walks through your object field by field: name, age, inventory, list, whatever it has, and encodes each value according to a defined format. Numbers become fixed byte sequences or text digits, strings get linked, prefixed, or quoted, nested objects recurse into the same process. The output is a flat stream of bytes or characters with no pointers, no memory addresses, nothing tied to that one running program. On the read side, a deserializer parses that stream back in the same order, reconstructing a new object with the same field values, in the same program, a different program, or an entirely different machine years later. The object is gone, but its shape survives. Not all serialization formats are built for the same job. JSON is probably the one you already know: human-readable text, key-value pairs, universally supported, the default choice for web APIs because you can open it in a text editor and understand it instantly. XML is older and more verbose, but still common in enterprise systems and configuration files. Both are text-based, which makes them easy to debug but slower to parse and larger on the wire. On the other end, binary formats like protocol buffers or Protobuf and MessagePack trade readability for speed and size. They're compact, fast to encode and decode, and popular for high-throughput internal services talking to each other. Then there are language-specific formats like Python's pickle or Java's native serialization, which are convenient inside one ecosystem but risky and often unsafe the moment untrusted data or another language gets involved. So when does serialization actually show up? 3 places constantly. First, persistence, saving application state to disk so it survives a restart, game saves, user preferences, a document your editor reopens exactly where you left it. Second, communication. Anytime two systems that don't share memory need to exchange data, which is essentially every API call, every microservice talking to another microservice, every mobile app syncing with a server. The object has to leave one process and arrive intact in another. Third, caching and messaging. Systems like Redis or a message queue like Kafka store and move data between processes, and that data has to be serialized to sit in the cache or travel through the queue at all. The common thread: the moment data needs to leave your program's memory in space or in time, you need serialization. 2 things trip people up in production. The first is versioning. 6 months after you ship, you add a new field to your object. Old serialized data on disk doesn't have that field. Deserializing it can crash or silently produce a broken object unless you design for backward compatibility from day one with default values and optional fields. The second, more serious issue is security. Serializing data you don't fully trust, from an untrusted client, an old backup, a third-party integration, can be dangerous with formats that allow arbitrary code execution during reconstruction, like Python's pickle or Java's native serialization. Attackers have exploited exactly this to run malicious code just by handing a crafted file to a deserializer. The rule of thumb: never deserialize untrusted input with an unsafe format, and always plan for your schema to change. Let's bring it together. Serialization converts a live, in-memory object into a portable format, bytes or text, and deserialization reverses that, rebuilding the object somewhere else. You reach for it whenever data needs to survive a restart, cross a network, or sit in a cache or queue. Pick a text format like JSON when you need readability and broad compatibility. Pick a binary format like Protobuf when you need speed and size at scale. And be careful with language-native formats the moment untrusted data is involved. Design for versioning early because your data's shape will change before your users notice. That's serialization, a small idea underneath almost every system you use every day. Thanks for watching.